In this video, we're going to look at some examples of using the substitution method to evaluate integrals. So this first example is a pretty straightforward example. We have the integral from 0 to 1 of sine of 3 pi t dt. So notice that this integrand here is pretty close to a function that you know an antiderivative for. If we just had sine of, say, u, then I know an antiderivative for sine of u. So when we use our u-substitution here, what we're really going to do is adjust for the fact that we've got a constant times the variable on the inside of the sine function. So letting u equal to 3 pi t, taking the derivative here, we get du will be equal to 3 pi dt. Notice on the outside we certainly have a dt. We don't have a 3 pi, but remember for substitution we can adjust for any constants that we want, and we'll see how to do that here in just a minute. Alright, so the last thing we need to remember is that these values for our limits of integration are referring to values of t. We need to substitute these in for our expression for u here in terms of t, so that we get bounds out now are in terms of u, not in terms of t. So notice that when t is 0, we get u is also 0, and when t is 1, we get u is 3 pi. So now when we make our substitution, we need to make sure again that we have to adjust for the constant. Our du is going to go in for 3 pi dt. So I need a 3 pi along with my dt to make our substitution for the du. To keep everything equal, we also need to divide by 3 pi. Now again, since we have constants here, constants move nicely inside and outside of the integral sign. Don't have any issues with that. So I'll put a 1 over 3 pi on the outside to adjust for the 3 pi that we have on the inside to go along with the dt. So now when we make our substitution, the inside of the sine function is what we're calling u, and the 3 pi dt is what we're calling du. We notice we've also substituted in our limits of integration here. We've got a 0 for the bottom limit of integration and 3 pi for our top limit of integration here. And those are the values that correspond to t equal to 0 and t equal to 1. Now we need an antiderivative for sine of u. An antiderivative for sine of u is negative cosine of u. And we'll evaluate this at the endpoints. And now we'll use our fundamental theorem of calculus, plug in our upper limit of integration, and then subtract off what we get when we put our lower limit of integration. So we get cosine of 3 pi. Cosine of 3 pi is equal to negative 1. We also have cosine of 0, that's equal to 1. And then if we simplify this arithmetic expression, we'll get 2 over 3 pi for our final answer. Let's look at another example here. Let's say we have the integral of 2x squared plus 10 over the 4th root of x cubed plus 15x plus 2 dx. Now in this case we're doing an indefinite integral, so we don't need to worry about changing the limits of integration here. So if we're going to use a u-substitution to evaluate this, usually a rule of thumb is to look for a composition and let u be the inside of that composition. That's a general rule of thumb. Sometimes you have to be a little bit more creative than that, but that's a general rule for being able to evaluate an integral using substitution. Well, here I see a 4th root of this function. So again, I see the composition here in the denominator. So I'm going to let u equal the inside, let u equal x cubed plus 15x plus 2. When we differentiate, we get 3x squared plus 15 dx. In this case, I see a common factor of 3. When we factor out the common factor of 3 here, we get an x squared plus 5 dx. Now I don't quite see that in my numerator. However, notice that I can factor out a 2 in my original numerator and get a 2 times x squared plus 5, which is what we have here. So we can, again, play with constants, making sure that everything stays equal. We can play with the constants to get what we need for the du. As long as we have the function piece, we can always play with numeric constants without any issues. All right, so here I've just rewritten the 4th root as a 1/4 power, and here I've factored out the 2. All right, so to see where everything goes, we can take the 2 out in front. I need a 3 to go with the du. To adjust for that 3, I'm going to put a 1 over 3 out in front. So that's where the 2/3 is coming from. So then that 3 times x squared plus 5 dx is everything that's going to be in my du. Looking here now, my x cubed plus 15x plus 2, that's my u, and I've rewritten this as a negative 1/4 power. So finally, after we make our substitution, we get 2/3 times the integral of u to the negative 1/4 du. Now we can anti-differentiate this using our power rule. Add 1 to the exponent gives us 3/4. Doing 1 over that new exponent gives us 4/3. And then finally, at the very end here, we're going to plug in what u was. That was x cubed plus 15x plus 2. We have that raised to the 3/4. Multiply our fractions together, we get 8/9. And then don't forget, since we're doing an indefinite integral in this case, we want to make sure we have a plus c on the end. Let's do a third example here. This one it's asking us to do the integral from 0 to 2 of x over x squared plus 1 dx. Now in this case, it's a little harder to see what the composition is. There really is a composition here. It's just a little harder to see since I don't see, like in the previous problem, we had a fourth root of something, so we kind of saw what the inside and the outside were. In this case, the composition really is the reciprocating function here. I've got an x squared plus 1 in the denominator. So another thing to try is, if you're stuck on something with a fraction in it, let u equal the denominator and see if the derivative looks like the numerator. All right, so in this case, we let u equal the denominator, the x squared plus 1. The du then is 2x dx, and I really do see an x dx, and again, we can adjust for the 2. Like in our first example, we've got limits of integration we need to make sure we handle. When we plug in 0 for x, we get 1 for u. We plug in 2 for x, we get 5 for u. So now let's go ahead and make our substitution. Again, here, this first part is just adjusting that we have the 1/2 out in front to put the 2 with the x dx to give us our du. The denominator now is just the u. So after we make our substitution, we get 1/2 the integral from 1 to 5 of 1 over u du. 1 over u is something we know an antiderivative for. That's natural log of the absolute value of u, and evaluated at our endpoints. And then remembering that natural log of 1 is 0, we get a final answer there of 1/2 natural log of 5. Let's do another example here. We have the integral of secant squared secant squared of the square root of x over square root of x dx. Again, in this case, there's a couple of different compositions that you might see here. I've got a secant that's being squared, that's a composition. I've got the secant of something here, that's a composition. Or I could, like we said in the previous problem, maybe you wanted to let u equal the denominator. Well, letting u equal the denominator is not going to help us. Well, actually, it looks like we've let u equal the denominator here. Really what we're doing is letting u equal the inside of this composition, the square root of x. So when we do u equals square root of x, that's the same thing as x to the 1/2 power. Using our power rule to differentiate, du is 1/2 x to the negative 1/2 dx. Rewriting that, we get a 1/2 root x dx. And notice now the root x is in the denominator, which is exactly what we wanted here because we have a root x in the denominator in our integrand. We need to adjust for the 1/2 that we need for the du by putting a 2 out in front. So we get 2 times the integral, then we have the secant squared of root x, and then a 1 over 2 root x dx for our du. Making our substitution now, we get 2 times the integral of secant squared u du. An antiderivative for secant squared is tangent, so now we have 2 tangent u plus c. And then plugging back in what u is equal to, we get 2 tangent root x plus c. Let's do one more here where it's a little harder to see where the composition is. Let's say we wanted to evaluate the integral of e to the x over 1 plus e to the 2x dx. In this one, if you tried to let u equal the denominator, you would get a 2e to the 2x as your derivative for the du piece. Notice this is an e to the x by itself, not an e to the 2x. So that's letting the u equal to the entire denominator is not going to help us here. We have to be a little bit clever, and we can see it down here how I've rewritten the integral. This e to the 2x, we can use our properties of exponents to rewrite that as e to the x squared. And so now I see where that composition is. So using the idea of letting u be the inside of a composition, we're going to let u equal to e to the x, and then du is e to the x dx, which is exactly what we have here in our numerator. So, rewriting this first as 1 over 1 plus e to the x squared, and then times e to the x dx. Here's u, and here is du. So when we make our u substitution, we get the integral of 1 over 1 plus u squared du. And we recognize the antiderivative of that as inverse tangent of u plus c. And then finally, doing our reverse substitution, or plugging back in what u is equal to, we get inverse tangent of e to the x plus c.